have heard the name eigenvector? Okay. How many of you can actually write an equation for an eigenvalue problem?
Given the characteristic polynomial?
No, just the equation, the matrix equation that defines the eigenvalue problem. Okay, good. So help me. How can I write it? Let's say the matrix n by n matrix, the eigenvalues I'm the one looking for is matrix A.
So you find the determinant of A minus lambda I.
Well, the problem, the eigenvalue problem is this, right?
It's equal to lambda.
Right? Okay. So let's apply, let's say R is, A is actually the R B to A. And this is some vector P, let's say call it V, is equal to lambda times V, right? Right? And we have learned R actually has two meanings, one as an operator, the other one as a mapping, right? Let's forget about the operator part, let's say the mapping part. Let's say if we are looking at an operator now. So AR, B to A is an operator that operates on the vector V and produces another vector that is A, and lambda V, right? Right? Lambda is what? It is a scalar, right? Right? So lambda is a scalar. So what is this operation doing? Think about it. What is this operation doing?
Just mapping a vector into a new space.
So what it's doing is, it is taking a vector and actually just extending or contracting it. It's not making any rotations to it, right? That's what it means, right? There's no rotation here. It's just alpha times the vector v, right? So you took a vector v and you applied R b to a to this, and you got another vector in the same direction. It could be longer, or it could be shorter, or it could be in the opposite direction, but you are moving in this same direction, right? That's what it means, right? Everybody with me? And that's why this is an eigenvalue problem, because it extracts the characteristic directions from this matrix R, right? Now, what are the properties of R? So we now know that if you convert this to an eigenvalue problem, it shrinks or contracts the vector, right? So if V was an eigenvector, it only shrinks and it scales it without changing the orientation, right? Okay, so what are the properties of R? We know the properties of R by now, right? R is a rotation matrix, right? That means the individual columns are
Projections of
no. What are the properties of individual columns? If R B to A has these column vectors R1, R2, and R3, what are the properties of R1, R2, and R3?
They're the dot products of the x, y, and z vectors of the two frames.
All right. Which means that they are orthogonal to each other, right? Right? Which also means that the dot product is equal to
0.
0. That means that these three vectors, R1, R2, and R3, represent a coordinate system, an orthogonal, and actually orthonormal, because they are, the magnitude is 1. Okay. So, if going back to the eigenvalue problem here, if V is one of the eigenvectors, and we know if it is an eigenvector, it has to correspond to one of these values here, right? And so what it happens is that, and the question was, what is the, so if you want to find out the eigenvalues of this, basically there would be like minus I 0, 0, 0, 0 plus I 0, 0, and 0, 0, 1, right? These would be the eigenvalues of this matrix. And he is asking, what is the significance of this? Right? That was the question, right? What is the significance of the unit eigenvector? So I'm asking you, what do you think is the significance here?
No change in, yeah.
That means the rotation is about that unit vector, right? Because these, if you plot these on a complex plane, these would be one in this direction, the other one would be in that direction, and the other direction coming out is where this one is, right? So that's what it means, that the eigenvector 1 corresponds to the one that is about which the rotation is taking place. Okay? Okay. So much for the digression. So the question I have for you, and I looked at the class schedule that I had made for myself, and if you might have noticed that we are quite a bit behind the schedule, right? So my question to you is, what do you think is the pace of the class? Is it right? It is slow? Can we speed up a little bit? What do you think where we are, given how much material we have covered and how much lies ahead of us?
Compared to the other classes, this one is running a little slower.
Okay. Depends on the other class, right?
Right. But that's all the information I have to go off of.
Well, depending on the material that we have. And the reason I have adopted the pace that I have is because these are very fundamental. I can speed this up, but then, you know, it will be very difficult to kind of bridge the gap between, to catch up with the fundamentals. Then we will have to slow down at the end. So I'd rather start slowly, that you have a time to understand and grasp the material, and then pick up pace as we go along. Okay? So that is the idea behind it. But if you want me to speed up, I can do that. That's not a problem.
I'm not complaining.
Okay.
It's information to the other classes.
Okay. So anybody else has any opinion, ideas, concerns about the pace of the course? Okay, good. So where were we? Where were we last night?
I had a probably get 6 parameters from 12.
Okay. And any thoughts about that? So let's do a little bit recap here. So we said the homogeneous transformation B to A, we could write this as the matrix B to A, and then PV origin with respect to A, and 0 and 1, right? We said that this one gives us, so we need actually to fully specify a vector of orientation, we need XP and XR, where XP denotes the position and XR represents the orientation, right? And position, if we graphically, we can look at it this way. This is my frame A, and this is my rotated frame B here. And this vector here is my PB origin with respect to A. And then you have this rotation matrix that takes me from B to A. Right? Everybody understand this notation, right? So now, XP is basically is nothing but the coordinates of this vector here, which is, I'm going to write it as Px, Py, and Pz, right? And depending on the coordinate system, this could be different, depending, it could be a spherical coordinate system, it could be cylindrical coordinate system, but you will have three parameters that define the point. There is no ambiguity about where P, this PB origin to A is, right? Right? Okay. On the other hand, now XR, so for a rigid body, how many degrees of freedom does a rigid body have? And these are, excuse me. So we have 6 degrees of freedom, right? 3 of them are, okay, and the other 3 are what?
Petrano.
Angles,
Yeah.
right? Okay, so this, the first 3, the position parameters are pretty well defined here, right? How do we get to XR? So you are saying that this has some angles, let me call this for the sake of, representation, alpha, beta, and let's say gamma, right? Right? I can choose any parameters, as long as we understand that there are 6 degrees of freedom, 3 related to the position and 3 related to the orientation. We know what 3 related to the position are. The 3 related to the orientation, we just found out that there are 3 angles here. I'm going to represent them as alpha, beta, and gamma, right? Right? So where are these alpha, beta, and gamma? How do we get them?
From the rotation matrix.
Be the angle from
Well,
point to.
okay, so with rotation matrix, if you have a rotation matrix, what you have is a matrix that R B to A is a 3 by 3 matrix, right? So you have 9 numbers here, right? These are just any 9 real numbers. How do we get from this an array of 3 by 3 of real numbers to specific alpha, beta, and gamma? We know the information is embedded in here, right? Right? Dot product of axes is going to give me 0. I'm just asking all these questions. We will get there, but I'm just asking these questions to make you think a little bit. Okay. So let's look at it, see. So now we know the problem. The problem is, what is the problem? The problem is that we want 6 parameters, and we actually have how many? We have 12, right? So if I give you 6 equations, 9 equations, 12 equations, and 6 unknowns, you will find more solutions than are required, right? there will be, so there is some redundancy in this, and this representation of position and orientation. Okay, so how do we resolve that, is the question. So we said that the rotation representation R B to A. We could write this as this matrix of R11, R12, R13, R21, R22, R23, R31, R32, and R33, right? And I can write this as, for the convenience, vector R1, R2, and R3. These would be these vectors here, R1, R2, and R3. Okay? And these are actually what is called, what are the direction cosines. Direction cosines of x, and this is y, and this is z. Okay. So now, so R has, it has 9 parameters. And we need, from these 9 parameters, we need only 3. Okay, so that means that the 9 parameters in R are not independent. Right? That's what it means. So if all the information is embedded in these 9 numbers, and we actually need only 3, that means that these 9 numbers must have some relationships that makes them redundant. So we can actually say, so what are these, so what are the properties of these? What do we know about the norm of R1? The norm of this vector here? And the norm of vector 2, and the norm of vector 3. They are all equal to 1. Okay. What about, there's the other, what is the other property of R? R has just 2 properties.
The dot product of its vectors.
Okay, so the dot product between any Rij is equal to what?
0.
Is 0. Where Ij equals 1, 2, and 3, right? I could also write this as Ri equal to 1, where I is 1, 2, and 3. Okay, so these three are the three, so these are three equations right there. These are three equations right there, right? And so, so we had 9 minus 9 parameters minus 6 constraints, right? Gives you what?
Three of free?
3 degrees of freedom. Right? Everybody with me on this? So now, going back to the rigid body, has 6 degrees of freedom, 3 corresponding to position and 3 corresponding to orientation, right? And since we have 9 parameters in the R matrix, and they are related, constrained by 6 constraints corresponding to normality and orthogonality, gives us 3 degrees of freedom for the rotation matrix, for the orientation of the rigid body in free space. Okay? Everybody understands that? Okay. Okay, so the matrices that actually have this property here are said to belong to a group of SO3, where this is a class of matrices of all 3 by 3 matrices that have these properties, and it's called a special group. What is it called? This is called special group of orthogonal matrices. It's called SO3. So you can say the matrix B to A belongs to a group of SO3. Okay, if you read the literature, they will say this and move on. So now when you see that RA belongs to SO3, you know what it means, right? And it belongs to all group of matrices that have normal the columns are normal, means the norm of their columns is 1, and all the columns are orthogonal to one another. They correspond, all of these matrices correspond to rigid body rotations. Okay. So which brings us to some important conclusions here, that that means R is redundant. Is a redundant representation means the parameters in R are related to one another. Which means that R has too many solutions. Right? So it has, so now, you know, let's say you were able to solve these 9 equations somehow, and you come up with 9 solutions, right? How do you know which one is correct? How would you know? If R has too many solutions, how do you know which solution is the correct solution?
Aren't they all correct?
They are all solutions, so they are correct. But how do you know that which is the valid solution? Thank you, I know what you're saying. How do you know which one of these solutions is a valid solution?
What do you mean by valid solution?
Well, so let's say the valid solution would be that corresponds to the orientation of a rigid body, right? So what by valid, what I mean that if I can get alpha, beta, and gamma that corresponds to a particular orientation of the rigid body, and that comes out as a solution for the 9 equations, or how many equations we have, and we know that solutions are more than actually the 3 alpha, beta, and gamma that we're looking for. How do we know which one of these solutions which one of these solution is valid solution to get to alpha, beta, and gamma?
Would you just put more constraints on it? Maybe make them all positive numbers or less than pi or something?
Okay, so we know these 6 equations right here,
Yeah.
right? So once we find all the solutions, any of those solutions that do not correspond, that do not meet these constraints, is not a valid solution, right? That's what it means. So that means that if you were to solve these equations, every time you come up with a solution, you will have to, so your algorithm for solving this problem would be that you find the solutions for whatever means you want to find them, and for each solution you come back and verify the solution with respect to these 2 orthogonality and normality conditions, right? And any of the solutions that, a set that meets these 6 constraints would be the valid, right? So that's how you would, which is kind of a tedious way of doing things, right? Don't you think? Because in a robotic system, you have to solve for not just one orientation, you have to solve for a trajectory. So each one of these points here, you will have an R matrix associated with it, right? So you can now think of the complication that if you want to solve, and of course depends what is the granularity of your trajectory is. You're going from one point to the other point, you'll have to solve R 2 to 1, for instance. Then you'll have to solve for another R 3 to 2, right? So you can, so you know how difficult it would be if you just relied on your R matrix. R matrix is nice. It gives you the information that we need. It gives you the position and the orientation of the links, but it is not the best way of calculating. If you are interested in specific angles, then R is definitely not the way to do it. Okay. And that means that, you know, given that has too many solutions, and each solution must satisfy the constraints. And these constraints, what are these constraints? These are the normality, and the other one, orthogonality, right? Okay, that means that this way is not really practical. Okay, so now we know the difficulty associated with solutions through R is. So let's just go back and rethink of how we define angles.
I had a quick question.
Yes.
So if you have multiple solutions, why would any particular solution not be, not focal normality and the other constraint? Because you're saying it's a valid solution, so why wouldn't it make sense?
Well, if you think about it, you see the constraints are actually, constraint, you can think of the constraint as a surface, right? So when you solve it, there could be points all over the place, but the only valid solutions are the ones that lie on the surface. No, I didn't make myself clear. How else can I say this? Well, so we know that the system is redundant, right? Which means that it has more solutions than what we need, right? How can we define? How can we put? So you can look at the constraints as eliminating the extraneous solutions and focusing on a small set that represents the actual orientation of the body. Okay? All right. So let's look at the three angle representations. So that means actually we need to find, to represent angles in the three-dimensional, in the three space, right? So we need to find a way of representing angles in a three space, since R, even though it gives us the solutions, it is a redundant system, and we've already discussed the complications associated with eliminating the redundant solutions. Okay, so to address this representation problem for the orientation, there are two ways, actually several ways. The two of the ways to represent angles is what is called the fixed angle. So let's look at this. I'm going to draw here a line, and I'm going to call it fixed angle representation. And then you have the relative okay, so let's assume that you have a frame A here. This is your given frame A, and you want to rotate it to another frame B. So this is your initial configuration, this is your final configuration. So how do we go from A to B, right? So there are two ways of doing it. One way is to rotate about these original axes, let's say, X, Y, and Z. So you start by rotating about X, then you rotate about Y, and then you rotate about Z, till A corresponds to B. Can you see that? So you have these three knobs here. You rotate X, then you rotate Y, and then you rotate Z. Combination of these three rotations so that the final configuration corresponds to B, right? This would be equivalent to like if you have a vector that you can split up into its components, and then you add the components to get the final vector, right? So if you were to able to somehow find out ways to split the total angular rotations along X, Y, and Z, then you can rotate X, rotate Y, and rotate Z till the two frames are coincident, right? So this is called so you rotate about the original A axis to obtain B. Okay. The other one is what is called the relative angle representation. And let's say you have, again, you are given the frame A, and you are asked to rotate it to another frame B. So in this particular case, what you could do is that you rotate. Once you have rotated, let's say once you have rotated about X, if you rotate about X, your Y and Z will have a new, let's see if we apply the right-hand rule here, your Y and Z will have new orientations here, right? I'm going to call them Y prime and Z prime. Right? Once you rotate it about your x-axis, your y and z will have new orientation, right? Everybody with me in this? And so your new y and z axis would be, I'm going to denote it as y prime and z prime. So in the next rotation, instead of rotating it about your original y, you rotate it about the new y, which is the y prime. Right? So when you rotate about y prime, what happens to your z and x?
They also rotate.
They rotate. So your z and x, so z goes to, I'm going to call this z double prime, right? And x goes to another location, I'm going to call this x double prime. Right? Everybody with me on this? Okay, so the third rotation, instead of rotating it about the original z-axis here, I'm going to rotate it about the z double prime. And now when I rotate it about z double prime, I get the new rotation as, I get a new x triple prime and a new y triple prime. right? Everybody with me on this? So you start with X, gives you Y prime and Z prime. These were the new rotated axes. Then the second time you rotate about Y prime, it gives you Z double prime and X double prime. The third time you rotate Z double prime and you get X triple prime and Y triple prime. So you continue these combination of these rotations till you finally you go to your which takes you to your B, which is your final orientation of your axis, right? Okay. So we say rotate first about X, and if you rotate about X, you get Y prime and Z prime. Then you second, you rotate about Y prime, and you get X double prime and Z double prime. And third, rotate about Z double prime, and you get X triple prime and Y triple prime. Right? Okay. So it so happens that to go from A to B, you can have as many as 12 combinations of rotations. So to go from any orientation A to orientation B, you would at most need 12, there will be 12 combinations of these rotations that will take you from frame A to frame B. So, yes?
Is it 12 rotations or is it 12 movements?
12 combination of rotations. Combinations. We're talking about combinations, right? And then here you can also have 12 combinations of rotations. So you see, depending on whether you use your fixed angle representations or your relative angle representations, you will have about 24 different combinations that could result from going from frame A to frame B. But it also happens that these two actually are equal in representation. So any combinations that you find here, you can also find here. So in effect, there will be about 12 combinations of rotations that will take you from frame A to frame B. Okay? Okay. So if you want to go back and do this, so you have your fixed angles. this is your frame A, and then this is your frame B. So this is your initial configuration. And this is your final configuration. And then you have relative angles and these are 12 combinations here. And then you have your relative here that will take you from A to so that will means that this is your axis XA, and if you rotate about XA, you get YB prime and ZB prime, right? And this also gives you 12 combinations here. So the relative angles are actually called the Euler angles. Euler angle representation. And the fixed is, of course, the fixed. Okay. Let's look at an example here.
Quick question.
Yes.
Any reason it comes up to 12 combinations? Like, what's the intuitive way of realizing that, I guess? Why 12?
Why 12? It's because you have each one of them. Well, you can actually have people have found out that, you know, if you, for any two frames, you can have 12 combinations of getting from point A. Not all of them will be possible, but at most you will have 12, right? So you can get there from here to in two combinations, for instance. But maximum would be 12, right? So you have to go back and forth, start. If you have taken too many steps, you'll have to come back. And sometimes you don't go from here to there in one step. You'll have to, go back and forth. So if you're lucky, just one combination, one rotation would do it, but it would take, for a general rotation, 12 combinations. Okay. So let's look at an example here. And let's do the Euler angles first. And we will call this Z, Y, X rotation. That means that you first start with Z, then next time you rotate about Y, the new Y, and then lastly you rotate about the new X. Right? Okay. So this would be the relative angle representation. So let's say you are given, you rotate about z by an amount alpha, right? So you have this frame here, and this is xa, ya, and za. And you rotate about z by amount alpha, right? Can I put this down?
Good, okay.
So you get new, what do you get? What two new axes you get? X and Y. So you get your, I'm going to call this YB prime, and this is moved by amount alpha here, and then you have the new XB prime. This is also moved by amount alpha here, right?
The direction of rotation is always the same?
What
You're saying you're rotated by
Right
an
hand.
alpha, it's,
Right.
yeah, okay.
So, what would be the next step here? So how do I represent this rotation? Can I say that this is, I represent this by a rotation matrix which takes me from B prime to A? Can I say that? Yeah? What's that? Thank you. Can I say that? Right? And you know what this matrix looks like? What B prime to A looks like?
There's one in the lower left.
Lower right.
Lower right.
Sorry, lower right.
Good. So you know what this matrix. So you know what this matrix looks like, right? Should I write it? No, I'm not going to write it. 2. So you have now you what's the next step?
Rotate about Y prime.
YB prime by an amount, let's say call it beta. Right? So you had so you had this YB prime here, and you rotated about your YB prime by an amount beta, and you get new, what do you get? What do you get? ZB double prime and XB double prime, right?
Can I ask you a question about
Yes.
notation? So you're considering, after you make that transformation, you rotate about the z-axis on the first one, then that just becomes z single prime?
Yes,
Moving forward?
yes,
So that's why it's double prime now?
yes.
Okay.
Because we are rotating about a prime axis, so the new axis would be double prime, right? The first time we rotated about unprimed, we went to the first prime. Second rotation, we go from the first prime to the double prime, right? So what would be this rotation matrix looks like? I need the rotation matrix would take me from B double prime to
B prime.
B prime. Right? And you know what this matrix looks like? Right? Do we know what this matrix looks like?
One in the middle.
One in the middle, okay. And the other columns are betas, right? So this would be going back, this would be cosine alpha minus sine alpha, sine alpha, cosine alpha, 0, 0. Sorry. Why didn't anybody correct me?
That's right. That was right.
It is right. Right? This matrix, what does this matrix look like? This looks like, we know that it is rotation about y, so you have 0, 1, 0. And then you have
Cosine beta.
cosine beta 0, sine beta. You have minus sine beta 0, cosine beta, right? Everybody with me? Okay. Okay, so what's the last step? 3. This would be rotation about x b double prime by an amount, let's say gamma. Right? So you have xb double prime, and so what do you get? When you rotate it by amount gamma, you get two new axes of zb triple prime, right? And you get yb triple prime. Right? Everybody with me on this? And so I can then also represent my rotation matrix as b triple prime to b double prime. Right? And you know what that matrix looks like, right? Everybody with me on this? Right? Okay, so now I can actually do my B to A then, right?
B triple prime is B.
What's that?
B triple prime could just be B, because it's
Yeah,
the final
yeah,
frame.
yeah. Thank you. B to B double prime. So B triple prime is equal to B. Right? And so you know these three matrices, you multiply them, you get the final answer. Okay? So we can now represent B terms of what? In terms of alpha, beta, and gamma, which is what we wanted to do to begin with, right? Right? Did it solve our problem? Did it solve? Can we now? So you know how to calculate this, right? By this time you should know this. So given A to B, B to A, this combination is going to be a function of alpha, beta, and gamma, right? That was the original, what we wanted to solve. So I can write my B to A, Z prime, I'm going to write Z, when I say prime here, that means that I'm doing the Euler rotations here. So Z prime, Y prime, and X prime in terms of alpha, beta, and gamma, and I know I can do this by Z rotated by alpha, Y prime rotated by